Earlier this month, both John from Elmore Labs and myself joined Shamino and Safedisk from the Asus ROG overclocking team in their pursuit of finding the world's fastest Intel Alder Lake CPU. In pursuit of this goal, we used both liquid nitrogen and liquid helium. Liquid helium will cool the CPU down to minus 200 degrees Celsius, and it's thanks to those really low temperatures that the team managed to get a CPU frequency validation of over 7.5 GHz. They also achieved a PiFast benchmark world record. After the liquid helium session, we put the same system through its paces in the 3DMark CPU profile benchmark, and we achieved a near full sweep of benchmark world records as well. It's with this last achievement that I want to kick off this video. In this video, we detail the pursuit of finding the world's fastest Intel Alder Lake CPU. Sit back and enjoy. Released earlier this year in June, the 3DMark CPU Profile Benchmark introduces a novel approach to CPU benchmarking. Instead of producing a single number, the 3DMark CPU Profile Benchmark shows how CPU performance scales and changes with the number of cores and threads used. The CPU Profile Benchmark has 6 tests, each of which uses a different number of threads. The benchmark starts by using all available threads. It then repeats using 16 threads, 8 threads, 4 threads, 2 threads, and ends with a single threaded test. The 3DMark CPU Profile scores are a great way to check if your CPU is performing as expected. For overclockers, the CPU Profile shows the overclocking potential of your CPU and provides more ways to track and measure the gains from overclocking. For Alder Lake in particular, it's an interesting tool to compare its performance not only against the previous generation of Intel CPUs, but also against the highly competitive AMD Vermeer CPUs. Both John from Elmore Labs and myself had an interest in seeing whether Alder Lake could take the top spots in the various benchmark categories. At the moment of recording, the records in these categories were primarily dominated by the Intel Core i9-11900K. When reviewing these targets, we both immediately realized that the max threads category would be an unattainable record. The Core i9-12900K has 24 threads, which is far less than the 128 threads of the Ryzen Threadripper 3990X. The 1 thread to 8 thread categories, however, were definitely within reach, provided we'd be able to overclock the Core i9-12900K P-cores high enough to match the Rocket Lake records. From earlier pre-testing, we knew the Alder Lake overclocking capabilities were stellar, and the frequency would be sufficient to take on Rocket Lake. Add to matching the frequency an improvement in IPC, and there was little doubt these records would go down. The 16-thread category is an interesting one, not only because it is led by an AMD Ryzen 9 5950X, but also because it exposes us to Alder Lake's particular core configuration. The Alder Lake Core i9-12900K has a total of 16, so you think, well, each thread can run on its own core. Well, yes, but 8 of those are high-performance P-cores, and the other 8 are efficient but less powerful E-cores. Vis-a-vis the Ryzen 9 5950X, Alder Lake has a deficit to make up, as the 5950X has 16 high-performance Zen 3 cores. So, in order to have a shot at the 16-thread category, we'd need all of Alder Lake's IPC, plus high-frequency P-cores, plus high-frequency E-cores, and all that combined in a stable configuration. In the next couple of minutes, I'll show you the progress from the first tests to the eventual world records. Hope you enjoy. Our first attempt was with P-cores at 6.6 GHz, E-cores disabled, and ring at 5.9 GHz. We knew these settings should work fine, as these are the settings that also worked for other benchmarks like Geekbench. We used Windows 10 and ended up with scores pretty far away from our target.
Oh, I don't know, there's something weird where...
Did you do the AVX patch?
No.
I have it here.
Oh, was that the thing?
The main reason for our low scores was the AVX negative ratio offset acting up, or rather, not acting up. I will discuss the AVX behavior in another video, but to make a long story short, setting 0 AVX ratio offset does not give an offset of 0. Instead, Setting 0 made the AVX negative offset behave like Intel's default configuration. On Alder Lake, the negative ratio offset behavior is quite different from previous platforms. One of the differences is that by default, the CPU ratio, when AVX is active, will be limited to the maximum Turbo Boost 2.0 frequency. On the 12900K, that would be 5.1 GHz. That explains our poor benchmark results. Fortunately, this issue was uncovered in the days leading up to the overclocking event. So, we had a small software tool that would work around the default behavior and set an actual 0 offset. By the time this video is out, this fix will already be in the Asus ROG BIOS. A quick second attempt with the AVX ratio patch provided us with the evidence that everything was right. Yeah, that's the... Really? That's good enough.
Okay. So, can go home now.
Our score was now 1,434 points in the one-thread benchmark and already beating the current world record. Knowing that we were on the right track, we could now increase the frequencies and push for higher scores. Our third attempt focused on utilizing the bi-core usage configuration method. This way we can configure a higher frequency for the one-thread and two-thread benchmarks, then gradually reduce the frequency for the higher thread count benchmarks. We set 6.9 GHz for up to 2 active P-cores, 6.8 GHz for up to 4 active P-cores, and 6.7 GHz for up to all active P-cores. We also enabled the per core ratio limit configuration in case we want only specific cores to boost to the maximum of 6.9 GHz. With hopes extremely high, we set up the BIOS, booted into the operating system, made the necessary adjustments to the configuration using our special tool, then loaded up the benchmark and... let's see, all benchmarks.
This? I'm curious how this is doing.
That's really a lot lower. Did you set the AVX?
Yeah.
Failed. With a one-thread score of 1,174 points, we were further away from our target than ever. It took us a while to figure out what had gone wrong. Turns out the error was located between the chair and the keyboard, as we had forgotten to set the per core ratio limit higher than 54x. Hashtag fail. For the fourth attempt, we set the per core ratio limit to 70x to have plenty of headroom, and the score was still not good. Right, AVX patch. In attempt number 5, everything came together, and we achieved new world records in 1-thread, 2-thread, 4-thread, and 8-thread categories.
There we go.
Yep, there you go. So 1-thread, 2... The configuration was still the same as in our third attempt. 6.9 GHz for up to 2 active P-cores, 6.8 GHz for up to 4 active P-cores, and 6.7 GHz for up to all active P-cores. But, obviously, we wanted more. Can you get 2,000 points more?
Doing 16 threads?
Yeah.
No. The only thing I can try is to enable the E-cores again.
Yeah.
And see how that does, right?
In order to achieve better performance, we had two ideas. 1. Enable the E-cores. 2. Disable hyperthreading. This configuration would give us 8 P-cores and 8 E-cores, totaling 16 threads on 16 real cores. Leading up to the 6th attempt, we started testing the performance with the E-cores enabled and hyperthreading disabled. We ran a conservative 6.8 GHz for all P-cores, 5.4 GHz for all E-cores, and 5.9 GHz for the ring. In our first quick test, the 16-thread score improved by about 800 points from 13,022 points to 13,875 points. The 8-thread test only marginally improved from 10,830 to 10,841. This gave us good evidence for using the real E-cores versus the hyper-threaded P-cores for 16-thread performance. For our full 6th attempt, we increased the P-core frequency from 6.8 GHz to 6.9 GHz and ended up improving the 2-thread, 4-thread, and 8-thread scores. However, the 16-thread result was still more than 1,500 points away from the current record. In preparation for the 7th attempt, we first increased the frequency for up to 2 cores to 7 GHz. This passed the 8-thread benchmark. Then we further increased the P-core frequency to 7.1 GHz for up to 5 active P-cores and 7 GHz for up to all 8 active P-cores. Unfortunately, this did not pass the complete benchmark as the system crashed when running the 4-thread benchmark. In the full 7th attempt, we set the P-core frequency to 7.1 GHz for up to 4 active P-cores and 7 GHz for up to all 8 active P-cores. We also bumped the E-core frequency slightly to 5.5 GHz and maintained the ring frequency of 5.9 GHz. Passing 7.1 on 4 cores.
Yeah, actually it's quite it's very light.
Ooh, 1.5, 3. Yeah, this is good.
6.3, 1.5 seems to be all the benchmarks. Yeah. And what's 11? Okay.
We had 11.3, I think.
Really? Huh?
Yeah. This resulted in further improving our records, surpassing 1,500 points for 1 thread, 3,000 points for 2 thread, and 6,000 points for 4 thread. The 16 thread score also improved to 13,902 points. However, we were still more than 1,000 points away from the record. But we had one more trick up our sleeves. Windows 11. The 8th attempt would be a straightforward one. Simply apply the settings we know are stable from Windows 10 and check the result. So we set the P-core frequency to 7.1 GHz for up to 4 active P-cores and 7 GHz for up to all 8 active P-cores. We set the E-core frequency to 5.5 GHz and the ring frequency to 5.9 GHz. Press the Run Benchmark button and it crashed on the 2-thread benchmark. So nothing left to do other than reboot and try again. For the 9th attempt, we kept the same settings and this time it failed on the 4-thread benchmark. For attempt number 10, we decided to lower the P-core frequency to 7 GHz for all cores and increase the CPU voltage a little bit to 1.75 volt. Fortunately, this passed the benchmark. Since we lowered the frequency for the lower threaded benchmarks, our scores were lower than before. However, the biggest shock was the 16-thread benchmark result, which now showed 14,937 points. 1,000 points more than Windows 10, and most importantly, we were now within striking distance of the 16-thread record. That said, this system was pretty maxed out already. For attempt number 11, we tried increasing the E-core frequency to 5.6 GHz and the ring frequency to 6 GHz, but that failed. Then we reduced the frequency of one E-core cluster back to 5.5 GHz. This passed the 16-thread benchmark and yielded a score of 15,264 points. So close, yet so far away. Next step, increase the E-core cluster to 5.7 GHz. That failed the benchmark before it even started. So back to 5.6 GHz for the E-cores and increase the ring frequency to 6.1 GHz. That failed even faster than the previous try. So put the ring back to 6 GHz and try BCLK overclocking. We first tried 100.5 MHz BCLK. Fail. Okay, let's try 100.2 MHz base clock frequency. Fail. Okay, let's try more CPU voltage and increase it from 1.75 volt to 1.80 volt. Fail. Well, since we're now at a higher CPU voltage, we might as well try 7.1 GHz for up to 4 active P-cores again. Fail. Try again. Fail. Try lower CPU voltage, back to 1.75 volt. Blue screen. Okay, so clearly the number 11 is at fault here, so let's just straight go to attempt number 12. However, we still needed to figure out how to get this system stable. In preparation for attempt number 12, we went back to the drawing board. First, test with 1.75 volt, the P cores at 7 GHz, the E cores at 5.6 GHz and 5.5 GHz, and the ring frequency at 6 GHz. That failed. Then we changed which E-core cluster runs 5.6 GHz and increased the base clock frequency to 100.2 MHz. That passed the max thread benchmark, but failed the 16-thread benchmark. So we increased the CPU voltage again to 1.80 volt. That failed. Then we tried the same settings but with a CPU voltage of 1.70 volt. That failed. Then we tried to lower the frequency of all E-cores to 5.5 GHz and a CPU voltage of 1.75 volt. Now, I'm not sure if you've been counting, but this was the 15th try since our successful 10th attempt. We were getting annoyed and figured the system really is at the edge of stability. We were losing hope of getting the record in the 16-thread benchmark. However, this run was good. It passed max threads, then 16-thread, then 8-thread, 4-thread, 2-thread, 1-thread. It was good. Yep, we got it.
Yeah.
Yep, 15.4. Nice.
That has all the...
Everything. Everything we wanted to do.
Yeah.
15,411 points, a new world record. So, what do you do when you finally got the record? You try for more. Yeah, this has everything, man. It's like one run, just save it as everything. And now let's try base clock.
So just call this one everything.
For attempt number 13, we again increased the base clock frequency to 100.4 MHz. That failed. So back to 100.2 MHz BCLK and increased the P-core frequency for up to 5 active P-cores to 7.1 GHz. Then we also used the per core ratio limit function to allow only the strongest cores to boost to 7.1 GHz, while the weaker cores remain limited to 7 GHz. This passed the max thread benchmark, but failed the 16-thread benchmark. But if it fails once, then maybe it passes the next time. So try again. And this time it was good. It passed max threads, then 16-thread, 8-thread, 4-thread, 2-thread, 1-thread. It was good. It was great. In this final run, we managed to beat all our best scores except for the 16-thread. 1,544 points for 1-thread, 3,070 points for 2-thread, 6,092 points for 4-thread, 11,457 points for 8-thread, 15,394 points for 16-thread, and 15,394 for max thread. And what do you do when you pass the benchmark? You try again. For attempt number 14, we tried 100.4 MHz BCLK. That failed. Given we realized the system was absolutely maxed out at this point, for attempt number 15, we decided to give the same settings as attempt number 13 a go. This helped us improve marginally the 2-thread benchmark record with a score of 3,074 points. While we were definitely running the system at the absolute limit of stability, the benchmark passed. And you know what that means? You go again. For attempt number 16, we tried increasing one E-core cluster to 5.6 GHz. This passed max threads, but failed in the 16-thread benchmark. At this point, we called it a day and decided to tear down the system while it was still healthy. A good general rule of thumb is that you want to finish an extreme overclocking session with all the parts in your system still working. Knowing when to call it is an important skill of an extreme overclocker. At the end of the day, we achieved what we set out to do. Take all world records in the 3D Mark CPU profile benchmark from 1-thread to 16-thread. We improved the 1-thread to 8-thread records previously held by Intel Rocket Lake by 7 to 8%. And we improved the 16-thread record previously held by AMD Vermeer by less than 1%. So, 5 world records made a very good end of the day. As I already mentioned, this system had earlier in the day been used for the Liquid Helium CPU frequency overclocking attempts as well. As is tradition, with every new CPU, the ASUS ROG overclocking team will try to achieve the highest possible frequency on launch day. Of course, this requires extreme cooling like liquid nitrogen, or if the CPU works below temperatures of -200 degrees Celsius, even liquid helium. Shamino from ASUS ROG and Elmore from Elmore Labs are two of the most experienced people when it comes to overclocking with liquid helium. Together, they were behind the 7.3 GHz Rocket Lake, 7.7 GHz Comet Lake, 7.6 GHz Coffee Lake, 7.5 GHz Kaby Lake X, 7.3 GHz Kaby Lake, and 6.8 GHz Skylake overclocking records. With so much experience, the two have a tried and tested process. First, the ASUS ROG team sorts through the available CPUs to find at least one with promising overclocking parameters. The main parameter is, of course, how high the CPU can be overclocked. But other things matter too, like whether the CPU has a cold bug or cold boot bug, how well it scales with voltage and temperature, and how easy it is to reproduce the maximum frequency. Then, the team sets up a system and practices the validation process using liquid nitrogen. The system is put together and various strategies are tried. Ultimately, the goal is to have a specific process and a set target for the liquid helium session. That's because liquid helium is very expensive, so there's not much room for error. Finally, when everything is set up and ready to go, the hard work begins. The system first gets cooled down to minus 196 degrees Celsius. Typically, you would load a custom BIOS profile with all your settings saved. The settings are mostly to ensure the system can boot and operate at low temperatures, but do not usually include high frequency settings. Then, when you're in the operating system, you can use a tool to configure the high voltage and frequency for the record attempt. You'd primarily use the CPU ratio to increase the CPU frequency, but ASUS also uses an external hardware tool to increase the base clock frequency in small steps. This helps eke out the last 20 to 50 MHz. The last requirement is, of course, the liquid helium to cool down the CPU as far as it will go. On the first attempt, the team was unable to get a CPU frequency validation before the system locked up.
It's locked. It's locked.
OK，我关了。
Fan not running, like it's not doing anything.
It's running, but it's not very.
The lockup was caused by the temperature, which was minus 220 degrees Celsius and too low. This is called a cold bug. When they tried restarting, the system would not boot up, also due to too low temperature. This is called the cold boot bug. The fastest way to get the system back up and running is by using a torch and heat up the copper container mounted on top of the CPU. After a couple of minutes, the system was ready to go again.
Let me know when you're ready.
I'm ready. So I'll try 7.5 now at 210. I mean, why is this not on? Like, can you increase the not at the power supply? It's going to increase the power supply. Can you move it here?
No.
This no power supply.
I'm there.
Not quite, but
Slow now.
okay, I'm gonna try it here.
Okay.
Right. Plus one base part. Try on. Okay, that's 7.5. One more. Okay, locked.
Okay, not from the helium, I don't think. I was about that. Was it?
Yeah,
not
210. Yeah.
On the second attempt, the team reached 7,521.98 MHz before the system locked up. This time, the lockup was not caused by the temperature, but simply by system instability. As it looked like there was still a little more room to it, it was time for one last attempt. The third attempt had a rocky start to it. Even though the helium was flowing, the temperature got stuck around minus 206 degrees Celsius. The culprit was pieces of ice inside the container. After a little quick DIY work, the issue was resolved and the attempt got underway.
Remove it. Cooling now.
Yeah.
Yeah.
I don't know, there was some weird stuff in the container.
What's the target? 215, right?
Yes.
继续流，继续流。
Oh. Or if we want to get footage before, I want to make sure that we have a.
The final result is a CPU frequency of 7,543.95 MHz. The team wanted to give it one last go, but this time luck ran out.
Really? What?
You can't see anything. There's smoke.
Move the meter.
It's locked. It's like 221.
Handling liquid helium for overclocking at the extreme edge of stability is a difficult activity that will challenge even the most experienced overclockers, especially when the CPU has a cold bug and cold boot bug to manage. After the CPU frequency validation, it was time for the PiFast world record attempt. PiFast is a small software application to compute the number pi with a very large number of digits. Moreover, the application is used by overclockers as a competitive playing ground for over 2 decades. It is one of the benchmarks that is eligible for global points at HWBot and is therefore one of the important benchmarks for overclocking record attempts. The benchmark world record at the time was 8.28 seconds with a Core i9 11900KF at 7178 MHz. As I mentioned already, the same 7.5 GHz system was used for the PiFast world record attempt. The crucial ingredients for a PiFast world record attempt with Alder Lake are 1. Obviously high P-core frequency, preferably cooled by liquid helium. 2. Make sure to run the benchmark on the best core. And 3. Use Windows XP. I have some footage of the record attempt, so sit back and relax.
Stop cooling. I know. Okay. Okay. So cool down again.
开了吗？开了。来。
Two base four.
要再大吗？等一下，这样可以。
So
Yeah, cool.
you wanna go colder than 210 or you wanna?
210. Maybe 212.
It was pretty good control now. Like it was perfect, like staying for the screenshot. Going down pretty a good pace. Back of it.
关了要讲哦。我要关了。再
Okay, I'll run it.
关了。哎，小美，为什么你是关那个？啊？我是啊，因为你没有加入啊。
Same, right?
Same score.
OK， 来，开。
No need.
Same.
Okay, locked.
The final result is a PiFast score of 8.03 seconds with a CPU frequency of 7.3 GHz. Safedisk had possibly the most challenging assignment of the day, as he aimed to take down the Ryzen 9 5950X in Geekbench 3 and Cinebench R20. Both benchmarks proved to be a tough ground for the Core i9-12900K Alder Lake. While Safedisk got close, it was not possible to beat the AMD Ryzen in these benchmarks. The final result was 15,021 points in Cinebench R20. Once more, I'll leave you to enjoy the footage from Safedisk's Liquid Helium session.
Cinebench wait 215, then start run, okay? Because Cinebench heavy.
来了吗？
还没有，还没有。Go.停！
好，停。
停！
停了。
等一下啊。
情绪已经往下掉了。
Too far, Cinebench. Everything's too far.
At the end of a couple of exhausting days, the team walked away with a CPU frequency of over 7.5 GHz, a potential PiFast benchmark world record, and a potential 5 world records in 3D Mark CPU profile. Not bad at all. Assuming no one did better overclocking results between the session that we did and the time I'm uploading this video, this will effectively be the world's fastest Intel Alder Lake system. Well, that's it for this video. I want to thank Peter from Asus ROG for inviting me over for this Liquid Helium session. I will be uploading more regular content on Alder Lake in the coming days and weeks, so stay tuned for that if you want to see more overclocking guides with Alder Lake. And until then, have a nice day.